Let's explore CAP Theorem. We'll cover what CAP Theorem is, how CP and AP systems work, CAP at production scale, when to choose CP versus AP, and CAP failure modes and edge cases. Let's get started. So imagine you're building a shopping app with servers in California and Virginia. A user updates their cart in Virginia, and milliseconds later, another request from that same user hits California. Should California serve the request immediately with potentially stale data, or wait to confirm the latest state from Virginia? CAP theorem describes three properties. Consistency means every read gets the most recent write. Like if you write balance equals 100, then any read must return 100, never an older value. Availability means every request to a working node gets a response within your latency target, typically under 100 milliseconds. And partition tolerance means the system keeps working when network failures prevent nodes from talking to each other. Here's the problem. When a network partition happens and your databases can't sync with each other, you're forced to make a choice. Since partitions are inevitable in real systems, routers fail and cables break, you can't have all three properties at once. So you're choosing between CP systems that refuse some requests during partitions to stay consistent, like a banking system that won't let you withdraw if it can't verify your balance across all nodes, or AP systems that serve all requests but accept temporary inconsistency, like a social media feed that might show slightly stale posts but never goes down. The key insight is that network partitions are inevitable, so the real choice is whether your application needs strong consistency or high availability during those failures. CP systems choose consistency over availability using leader-based replication with protocols like Raft or Paxos. A single leader accepts all writes and replicates them to followers, only committing when a majority acknowledges. In a 5-node cluster, you need 3 nodes to form a majority. That's the leader plus 2 followers. The leader waits for at least 2 follower acknowledgements before returning success to the client, guaranteeing the data is safely replicated. During a network partition that splits the cluster into 3 nodes and 2 nodes, only the 3-node side can form a majority and continue operating. The isolated 2 nodes refuse writes and return errors. Availability drops, but the system never creates conflicting data. The latency cost is real. Within a region where round-trip time is 1 to 2 milliseconds, writes might cost 5 to 10 milliseconds at P99 because you're waiting for follower acknowledgements. Cross-region, where RTT is 50 milliseconds, each write takes at least 50 to 150 milliseconds. AP systems choose availability over consistency, using leaderless replication like Dynamo or Cassandra. Data replicates to N nodes, commonly 3, and you configure write consistency W and read consistency R. Setting W equals 1 and R equals 1 gives maximum availability. During partitions, all nodes continue accepting requests locally. If one availability zone loses contact with 2 others, clients in the isolated zone still get sub-10 millisecond responses. The trade-off is temporary inconsistency. Writes in the isolated zone won't immediately appear in the other zones. So here's the trade-off. CP systems like MongoDB use majority quorum, giving you strong consistency and no conflicts, but writes take 5 to 10 milliseconds, and you lose availability during partitions. AP systems like Cassandra give you 1 to 2 millisecond writes and stay available even when most replicas are unreachable, but you get stale reads and need to reconcile conflicts later. Here's a common misconception. CAP only applies during network partitions. When the network is healthy, many systems provide both strong consistency and high availability. Google Spanner, for example, achieves 99.999% availability, while maintaining strong consistency by adding just 5 to 10 milliseconds of latency for consensus within a region. So here's the thing about CAP theorem in real production systems. You don't make one global choice for your entire platform. Instead, you split your system into subsystems, and each one makes its own trade-off based on what that data actually needs. For payments and orders, you choose CP semantics because correctness is non-negotiable. Double charging a customer or overselling inventory costs you money and trust. The primary database waits for confirmation from at least 3 out of 5 replicas before acknowledging a write, which means if there's a network partition and you can't reach enough replicas, the system rejects new orders rather than risk inconsistent state.
Here's what that consistency costs you. CP writes with majority acknowledgement run at 15 to 30 milliseconds P99 latency within a region, and at 200,000 requests per second peak traffic, every extra 10 milliseconds of latency directly costs you throughput and capacity.
For your product catalog and recommendations, you go with AP semantics because slight staleness is totally acceptable. If a product went out of stock 2 seconds ago and someone still sees it available, that's fine. Data replicates across 3 availability zones asynchronously, and during a partition isolating one zone, all zones keep serving requests with P99 read latency of just 10 to 20 milliseconds. Modern systems like DynamoDB and MongoDB let you tune consistency per operation, not as a system-wide setting. For session storage, you default to eventually consistent reads at 5 milliseconds P99 for normal browsing, but when the user hits checkout, you request strongly consistent reads at 15 milliseconds P99 to ensure you have their latest cart state, even though that might fail during partitions.
When you're building a distributed system, you've got to choose between CP and AP. And it's not about which one's better. It's about matching the system behavior to what your business actually needs and what users expect.
Choose CP when mistakes are expensive or dangerous, like financial transactions where a duplicate charge violates regulations and costs real money, or inventory systems where overselling concert tickets creates customer service nightmares, or configuration management where inconsistent feature flags across servers can break functionality or create security holes.
The cost of CP is concrete. During a network partition that isolates 40% of your nodes, those nodes return errors because they can't reach the majority. If the partition lasts 5 minutes, users hitting those nodes see a 100% error rate, and your overall availability might drop from 99.99% to 99.5% during incidents. Choose AP when speed and availability trump perfect accuracy. Like social feeds, where users care that something loads in under 100 to 200 milliseconds, and missing the last few posts temporarily is totally acceptable. Or recommendations, where showing slightly stale results beats showing nothing. Or metrics and logging, where losing a few log lines is preferable to blocking writes. The cost of AP is subtle. You need conflict resolution logic, because with last write wins, clock skew of 200 milliseconds between regions can cause lost updates. And with version vectors, you need application logic to merge conflicts, like combining shopping cart items from different replicas, which adds real complexity to your code. Split brain is one of the nastiest failure modes in distributed systems. It happens when a network partition causes both sides to think they're the majority, and both sides start accepting writes, creating completely divergent histories that are really painful to reconcile.
Proper CP systems prevent split brain using term numbers or epoch counters. Every time there's a leader election, the term increments, and nodes reject any requests from leaders with stale terms, so only the legitimate leader with the highest term can actually write data. Here's a tricky problem. CAP assumes the network is either working or completely partitioned, but reality is messier. When your round-trip time spikes from 1 millisecond to 500 milliseconds because of network congestion or a garbage collection pause, your system with 200 millisecond timeouts thinks there's a partition and starts failing requests or electing new leaders.
The fix is adaptive timeouts.
Instead of a fixed 300 millisecond timeout, you use 3 times your recent P99 round-trip time, so the system adjusts to current network conditions and doesn't treat every latency spike as a total partition. AP systems using last write wins have a subtle data loss bug. If 2 clients in partitioned zones update the same shopping cart and one zone's clock is 200 milliseconds behind, the system picks the higher timestamp as latest and silently discards the other write, so users lose items from their cart. So to recap, proper CP systems use term numbers to prevent split brain, adaptive timeouts reduce false partition detection, version vectors catch conflicts that timestamps miss, and PaceLC extends CAP by capturing the latency versus consistency. That covers the CAP theorem. If you enjoyed this video, hit subscribe for more system design fundamentals. Thanks for watching.